In this video, we are going to implement a minimal hardware-based processor design. In particular, we'll use the Microblaze processor and implement it on a Basis 3 FPGA board. In some ways, this is an extension of the design that was presented purely in software simulation. Over here, we are going to concentrate only on hardware implementation and the aspects related to that. We'll be using the Microblaze, but implementing it for the hardware implementation on the FPGA. We will add a UART peripheral for communication with the outside world and add appropriate pin connections so that it can actually work in practice. Discuss briefly the address map and how the UART gets connected to the Microblaze and how we can communicate with it. And also how we start up the SDK, write programs with the SDK and get them executed on the Microblaze so that we can get the output on a serial port terminal. We will start by invoking Vivado as usual and creating a new project. Call the project hello. Of course, it could be anything at all. RTL project. We will specify sources later. Over here, I am going to go ahead and select the board using the Basis 3 board that we had discussed earlier. If you want this to happen, you need to have followed the instructions on the Digilent website to add the Basis 3 board as one of the accepted boards. If not, of course, you can still go ahead and add it as one of the parts that we used in the previous demos. This just makes things a little bit easier in terms of which pins get connected where. Create a block design. We can call it anything. I'll just call it MB for a Microblaze. And what I'm going to do is click plus to add IP, select the Microblaze processor module, double click, it adds the IP, and now it gives the option for run block automation. I'll select that. The only thing that I want to change over here is the local memory. Rather than being 8 kilobytes, I'm going to change that to its maximum that is allowed, which is 128 kilobytes. This becomes useful because some of the programs that we want to run later on the system are going to use up a decent amount of memory, and we would like to have a reasonable set of options for that. So we can set that to 128 KB. You can leave all the options alone. If you want, you can play around with the cache configuration. I'm leaving all of that at the default for now. Now, before running connection automation, there are two other things I want to do. One of them is in the clock wizard. Right now I can see that the signal has been shown as clock_in1_d, which is a differential input signal. Let me just double click on the clock wizard, and over here I'm going to select clock in 1 and say board interface, set it to sysclock, and the external reset in, set it to reset. This will automatically result in both of these signals getting connected to the appropriate pins. I will not need to do the explicit IO planning later, so it just makes life a little bit easier. The clocking options, I'm going to leave all of them at the default values. The input frequency is assumed to be 100 megahertz, and so is the output frequency. There's one more thing I want to do before running connection automation, which is add another IP. I'll select the UART Lite. Now, the UART Lite needs to be connected to the Microblaze. In order to do that, the AXI slave interface of this needs to get connected to the AXI interface of the Microblaze. That can also be taken care of by running connection automation. I'll just select all of these. What will end up happening is that the AXI UART Lite will get connected. The clock wizard as well as the reset, all of them will be connected appropriately. So you can see that all the connections have worked out properly. The reset signal for the clock wizard as well as for the reset clock wizard, both are connected to the system reset. The sys clock comes from outside, and the USB UART is taken as an external set of pins which is connected out here. I can just rearrange the drawing so it looks a little neater, and we are done. We can basically validate the design, find that there are no errors, and save it. Save this design, go to sources, right click on the MB block design, create the HDL wrapper. All of these instructions are pretty much exactly what you would follow even when you were creating the design for simulation. So I'm not going to go into any further details on those. Now we can go ahead and implement this. First I'm going to run synthesis. And now we have the synthesized design. We can open it. And what we would like to do is to look at the layout, I/O planning. In this case, we can see once we open that layout, we would see at the bottom in the I/O ports, all the ports listed in the block design are shown over here. So let's just go and verify. For example, the clock signal sys clock is connected to the package pin W5 and is set to the LV-CMOS 3.3 standard. Similarly, the reset signal is connected to U18, and the USB UART, RxD and TxD are connected respectively to B18 and A18. Now all of these are as expected and there are no unconnected ports, so everything is fine. We should be able to go ahead and generate the bit stream at this point. Before that, let's just quickly go back to the block design. There's one additional thing that I just want to point out over here. We have the Microblaze and we have one peripheral in this case, which is the UART Lite. The UART is basically the Universal Asynchronous Receiver Transmitter. It allows us to output data from the Microblaze and actually print characters onto the screen. And we can have a kind of a UART connector. In the case of the Basis 3 board, that connector goes through the same USB cable and allows us to display things on a computer monitor. Now, when you have a peripheral like a UART, you need to be able to talk to it from the Microblaze, and this is done by means of something called memory mapping. When we open up the address editor tab, we can see that there is a Microblaze, and when we click on the data portion, we find that there are two peripherals associated with it. One is the Microblaze local memory, the DLMB, which is the data local memory bus. It's a memory which starts at offset address 0 and goes up to high address of 1FFFF, that is 2 power 17, which corresponds to 128K. Similarly, we have one more peripheral, which is the UART Lite. It has a register offset. It is connected to the slave AXI interface of the interface interconnect, and it has a range of 64K memory locations starting from the offset address of 40600000 up to 4060FFFF. Now, this choice of 40600000 as a starting point is something arbitrarily made by the design system. You can change it if you want to, but unless there is a very good reason, you should probably just leave it at the default. All that is required is that when you start writing the software, you need to know this address so that you can communicate with the UART. Secondly, you might notice that you have an address range of 64K, that is effectively 65,000 memory locations associated with the UART. But if you recall what a UART actually does, all that you do is you transmit a single byte into it. It then sends that byte out serially. And on the other hand, when it receives data over the serial port, it converts it into bytes that can then be read back. So in terms of what kind of interface you need to talk to the UART Lite, you need only very few real memory locations. In this case, you will notice that the system has allocated 64K memory locations. That's just because those are available. We don't really need to sort of try and save on the number of memory locations. We can just allocate a large chunk of address space for this peripheral. And we do not really gain anything by trying to optimize this number of bits, which is why a large address range has been allocated to UART Lite. Of course, what you will see later is we don't really use most of it. On the instruction side, the only memory that is mapped is the instruction local memory bus. It has the same offset address and range as the data local memory bus. In other words, it tells you that the instruction and data are stored in the same physical memory and they share the same address space. Okay, now with all of that in mind, we can go ahead and generate the bit stream. Once the bit stream has been generated, we actually need to go through one more step before we go into the hardware manager. So we will just cancel this. And the next thing that we need to do is to export the hardware. In this case, since we have successfully generated a bit stream, let us choose the option include bit stream. And now we can launch the SDK. The SDK is the software development kit that we use in order to write programs that will run on the Microblaze. In our case, the program that we are going to write is going to be something relatively simple. All that we want to do is make sure that the serial port that we had attached, the UART that we had attached to the Microblaze is functional and that we can make use of it. Once the SDK opens up, you will notice that in the left Project Explorer pane, it mentions MB_wrapper_HW platform 0. The MB corresponds to the name that we gave to the block design, and MB wrapper is just a wrapper that is created around it. The hardware platform that has been created is specified in the middle pane over here. The target FPGA device is the 7A35T, that is the RTX used on the Basis 3 board. The address map for the processor Microblaze 0, as you can see over here, just as we saw in the address editor, there are two peripherals, the AXI UART Lite with this base address and high address, and the slave interface which is S_AXI, and the Microblaze local memory which has the base address of 0 and the high address of 1FFFF. You will also see that it lists out all the other IP blocks present in the design. In particular, the AXI UART Lite alone mentions what are the registers associated with it. All the others are pretty much standard peripherals. For example, there is a clock wizard, there is a debug module, there is an AXI peripheral interconnect, and the Microblaze itself. So in this case, if you really look at it, although there are all these IP blocks, they are not really peripherals connected to the system. They are all just supporting material. They are required for the system to work. Now, what do we do with this? What we would like to do is create a new application project. We can give it any name that we want. I'll just call it hello. Use the default location, OS platform, leave it as standalone. We are going to write standalone code, not using an operating system. The hardware target platform is the MB wrapper HW platform 0. There are a number of other predefined options. We are not going to make use of them now. The processor is Microblaze 0. That's the only processor available on this hardware platform, so you don't really have any choice over here. The language, we will use C for now. We will use C++ later, but for now we can just use it, leave it at the default value of C. It also asks for something called the board support package. This is something which contains additional software libraries to talk to the peripherals available in this board. We will just leave it at the default. It creates hello_BSP as the new BSP for this system. Click on next. It has a template called hello world that we will choose as our option, and click on finish. Now, if we go and open the tab corresponding to hello, we will see that there is a source folder over there where we can open the file called helloworld.c, which is actually a very simple piece of code. It basically includes stdio.h, platform.h, a new header file called xil_printf.h that you would not normally see in your C programs. And in terms of the code itself, what it has is there is something which does something called init platform, and at the end there is something called cleanup platform, and in between there is a command which says print hello world. Note that this is print and not printf. The reason for using print and not printf is because the print as well as another associated command called xil_printf are highly optimized and minimal versions of the print commands which send out bytes to be displayed on a serial port. You could have also used printf, but what you will find is that if you use printf, the size of the resulting program becomes so large that there is a good chance it won't fit within the 128 kilobytes of memory that you have. So we will always be using either print if you only want to print out a string, or xil_printf if you want to do some minimal formatting before printing it out. Alright, so now if you go here to the console, you will find that just the fact of creating the program has actually resulted in the entire build, that is to say the compilation of the program also being completed. So it says it was building this file helloworld.c using the Microblaze GCC compiler. This is the exact command which is run over there in order to compile it, right? As I said, these are all default values. You don't really need to change any of this. It finishes building it, and after doing all of that, it also compiles the platform.c and then invokes the linker, which puts all the different object files together and finally creates the hello.elf file which is going to run on the Microblaze processor. It also finally runs the command mb size, which tells you how big the program is. The important fact or the thing that you need to sort of look at over here is the text is the actual program code, 2712 bytes, 268 bytes for data, which is some internal variables that are being used. BSS corresponds to some functions which are being used within the main program, and the total file size therefore ends up being 6088 bytes. This is good because it is well within the limit of 128 kilobytes that we have set for our entire system. Now, in order to run this entire program, we need to do one additional thing, which is go back to a terminal, and I'm going to open up a new terminal, and I need to run some kind of a program that can connect to the serial port that the FPGA board is providing. On my Linux machine, I'm going to use a program called Minicom, but there are other programs. For example, there is something called GTK term, which you can use in order to connect to the specific board that you are using. Now keep in mind that whichever program you use, if you are using Windows, for example, there is something called Hyperterminal or another program called TerraTerm. In all of those cases, the main things that you would need to be concerned about is to find out the correct port corresponding to the device that you have plugged in. Unfortunately, there is no standard way of finding that out. On my Linux machine, it turns out that once I plug in the FPGA board, it creates a USB UART interface with the name /dev/tty/USB1. You can see that this device exists over here. It was created at September 18th at 3:39. The reason why it shows up at this time is this was the time when my machine was started, and when it boots up and it recognizes this device, it basically creates this peripheral corresponding to that. Okay, so what I'm going to do is to run Minicom, and it has already been configured to connect to port /dev/tty/USB1. In addition to this, at the bottom you can see that the speed setting has been set to 9608N1. 9600 bits per second is the rate at which data is being transferred over the serial port. 8 bits per character that is being sent on the serial port, no parity bit, and 1 stop bit. These parameters are pretty much standard. You don't really need to fiddle with them. The 9600 is something you might have to modify if you had made a change on the UART Lite while creating the Microblaze project to start with. Now if I go back here, I can go to this option run over here and select run configurations. I want to create a new run configuration that can be used in order to run this program. What I will do is select this option out here, Xilinx C++ application, which basically says to run or debug an SDK executable. If I double click on it, it creates a new option over here. It says GDB debugger on local. Debug type is standalone application debug. The connection is local. The hardware platform is the one that we had chosen earlier. The bitstream file, it has figured out the correct bitstream file automatically. If not, we can click on search, select the appropriate file and click OK. I will also select this option to reset the entire system and also to program the FPGA as and when I run the configuration. Let me select apply over here, and before clicking on run, there is one more thing. In the application tab, I am going to ask it to automatically download a certain program, and when I click on the Microblaze processor, it selects the project, and from that project it automatically selects which ELF file is available as a binary. All of those are done automatically, and it resets the processor. And now if I click on run, I'll find that down at the bottom I can see there are some messages corresponding to actually loading the bit stream, resetting the program, and everything has completed. It has even in fact disconnected. If I go back to the terminal here, I find that the message hello world has been printed. So this essentially was just a quick walkthrough of how you could set up a basic Microblaze processor system on the basis 3 board, connect it up to a PC, generate the bitstream file, generate a corresponding SDK code, that is the software development kit, set up the UART communication using a program such as Minicom or GTK term or TerraTerm on Windows. And once you have got all of that in place and you run the program from within the SDK, you can get the output onto the serial port terminal.